You have already explored what the OC model is, how encapsulation works, and what IP addresses and packets look like in practice. You even observed real network traffic with tools like Ping and Wireshark. Now it is time to go deeper into the foundation of all of this, the physical layer, known as Layer 1 in the OC model. Without Layer 1, no data can travel anywhere. Every packet you have seen, every IP address you have studied, ultimately depends on a physical signal being transmitted over some kind of medium. This chapter gives you the solid theoretical grounding you need to understand what happens at the very bottom of the stack. Layer 1 is called the physical layer. Its sole responsibility is to transmit raw bits, zeros and ones, from one device to another. It does not care about addresses, protocols, or meaning. It only deals with how to represent and move those bits across a physical medium. The physical layer defines the electrical, optical, or radio characteristics of the transmission, as well as the connectors, cables, and signaling methods used. Understanding this layer is not just academic. As a cybersecurity and DevSecOps professional, you need to know how data physically travels because certain attacks and vulnerabilities are rooted at this level. Passive eavesdropping on unshielded cables, signal jamming on wireless networks, or physical access to network infrastructure are all Layer 1 concerns. Knowing the strengths and weaknesses of each medium helps you assess risk accurately. What is a signal? A signal is a physical representation of data. When a computer sends a bit, either a 0 or a 1, it converts that bit into a signal appropriate for the transmission medium. There are two main types of signals used in networks. Analog signals. These are continuous waves that vary smoothly over time, like sound waves. In older telephone networks, voice data was transmitted as analog signals. Analog signals are susceptible to noise and degradation over distance. Digital signals. These are discrete signals that represent data as distinct values, typically high voltage for 1 and low voltage for 0. Modern computer networks primarily use digital signals because they are more reliable and easier to regenerate. When a digital signal travels through a cable, it can degrade due to interference, resistance, or physical imperfections. This degradation is called attenuation. The longer the cable, the more the signal weakens. Network standards define maximum cable lengths precisely to prevent data loss caused by excessive attenuation. Another important concept is noise, which refers to any unwanted electrical or electromagnetic interference that distorts the signal. Noise can come from nearby electrical equipment, other cables carrying current, or environmental sources. The ratio between the strength of the actual signal and the level of noise is called the signal-to-noise ratio. A high signal-to-noise ratio means the signal is clear and reliable. Transmission modes. Data can travel between devices in different ways depending on the direction of communication. Simplex. Data flows in only one direction. One device transmits, the other only receives. An example is a traditional television broadcast. Half-duplex. Data can flow in both directions, but not at the same time. Devices take turns transmitting. Old walkie-talkies work this way. Early Ethernet networks using hubs also operated in half-duplex mode. Full-duplex. Data flows in both directions simultaneously. Modern Ethernet connections using switches operate in full-duplex mode, which doubles the effective bandwidth compared to half-duplex. In the context of cybersecurity, understanding full duplex versus half duplex matters when analyzing traffic capture behavior and collision domains, especially when working with older network equipment. Physical transmission media. There are three main categories of physical media used in networks: copper cables, fiber optic cables, and wireless, radio frequency. Each has specific characteristics, advantages, and weaknesses. Copper cables. Copper cables transmit data as electrical signals. They are the most common type of cable in local area networks. There are two main types. Twisted pair cables. These consist of pairs of copper wires twisted together. Twisting the wires reduces electromagnetic interference between pairs. There are two subtypes. Unshielded twisted pair, often abbreviated UTP. No additional shielding around the wire pairs. It is the most widely used type in office environments. It is cheap and easy to install but more susceptible to interference. Shielded twisted pair, often abbreviated STP, has additional shielding, a metallic foil or braid, around the wire pairs or the entire cable. It offers better protection against interference but is more expensive and less flexible. Twisted pair cables are categorized into standards called categories. Category 5E supports speeds up to 1 gigabit per second over distances up to 100 meters. Category 6 supports up to 10 gigabits per second over shorter distances. Category 6A extends that 10 gigabit capability to 100 meters. Each category has specific physical specifications for the number of twists per centimeter, insulation quality, and connector standards. The standard connector used with twisted pair cables is the RJ45 connector, an 8-pin modular plug that you have certainly already seen when plugging a network cable into a computer or switch. Coaxial cables. These consist of a central copper conductor surrounded by insulation, a metallic shield, and an outer plastic jacket. Coaxial cables were widely used in older Ethernet networks, 10-base-2 and 10-base-5 standards, and are still used today for cable television and internet connections from cable providers. They are more resistant to interference than unshielded twisted pair cables. The main limitation of copper cables is their susceptibility to electromagnetic interference, their limited range, typically 100 meters for twisted pair, and the fact that the electrical signal can be intercepted using equipment placed near the cable, a significant security concern. Fiber optic cables. Fiber optic cables transmit data as pulses of light rather than electrical signals. They consist of a thin glass or plastic core through which light travels, surrounded by a cladding layer that reflects the light inward to keep it inside the core, and an outer protective jacket. There are two main types of fiber optic cables. Single-mode fiber has a very narrow core, typically around 9 micrometers in diameter, that allows only a single path of light. This enables transmission over very long distances, tens or even hundreds of kilometers, with very low signal loss. Single-mode fiber is used for long-distance telecommunications, backbone connections between buildings, and internet service provider infrastructure. Multi-mode fiber has a wider core, typically 50 or 62.5 micrometers, that allows multiple paths of light to travel simultaneously. This is cheaper but limits the maximum distance, typically up to 550 meters at high speeds. Multi-mode fiber is commonly used inside buildings and data centers. Fiber optic cables offer several major advantages over copper. Much higher bandwidth, capable of supporting speeds of 100 gigabits per second and beyond. Much longer distances without signal degradation. Complete immunity to electromagnetic interference. Significantly harder to physically tap without detection, making them more secure against passive eavesdropping. The main disadvantages are higher cost, greater fragility, and the need for specialized equipment and skills for installation and repair. Wireless transmission. Wireless networks transmit data using radio frequency waves through the air. There is no physical cable involved. The most common standard for wireless local area networks is Wi-Fi, which is based on the IEEE 800 2.11 family of specifications. Key concepts for wireless at the physical level. Frequency bands. Wi-Fi operates primarily on two frequency bands, 2.4 GHz and 5 GHz. The 2.4 GHz band has greater range but lower speeds and is more congested because many devices, including Bluetooth devices and microwave ovens, also use it. The 5 GHz band offers higher speeds and less congestion but shorter range. Channels. Within each frequency band, the spectrum is divided into channels. Choosing non-overlapping channels is important to avoid interference between neighboring networks. In the 2.4 GHz band, only 3 channels do not overlap: channels 1, 6, and 11. Signal propagation. Radio signals travel in all directions from the transmitting antenna. Walls, floors, and other obstacles absorb and reflect radio waves, reducing the signal strength. This is called attenuation, and it directly limits the range and reliability of a wireless connection. Security implications of wireless. Because radio signals propagate in all directions, anyone within range can potentially capture the radio waves. This makes wireless networks inherently more vulnerable to passive eavesdropping than wired networks. Encryption protocols, such as Wi-Fi Protected Access 2 or Wi-Fi Protected Access 3, are essential on wireless networks precisely because the physical medium is open by nature. An attacker does not need physical access to a cable to capture wireless traffic. Bandwidth and throughput. Bandwidth refers to the theoretical maximum amount of data that can be transmitted over a medium per unit of time. It is expressed in bits per second, kilobits per second, megabits per second, or gigabits per second. Throughput refers to the actual amount of data successfully transmitted per unit of time in real conditions. Throughput is always lower than bandwidth because of factors like signal noise, protocol overhead, and network congestion. For example, a network cable rated for 1 gigabit per second of bandwidth will typically achieve a throughput of around 900 megabits per second or less under real conditions. Network devices at Layer 1. Some network devices operate purely at Layer 1 and have no awareness of addresses or protocols. Repeaters. A repeater receives a degraded signal on one port, regenerates it, restores its original strength and clarity, and retransmits it on the other port. Repeaters are used to extend the maximum cable length in a network segment beyond what a single cable segment allows. They do not filter or interpret data. UBS, A hub is a multi-port repeater. When it receives a signal on one port, it retransmits that signal on all other ports simultaneously. Every device connected to a hub receives every signal sent by any other device. This creates what is called a collision domain. All devices share the same bandwidth and signals can collide if two devices transmit simultaneously. Hubs are essentially obsolete today, replaced by switches, which operate at layer 2 and are much smarter, but understanding them helps explain why switches were a major improvement. Encoding and modulation. Before bits can be placed onto a physical medium, they must be encoded into a signal format. Different encoding schemes exist. Non-return to zero, NRZ. A high voltage represents a 1 and a low voltage represents a 0. Simple but prone to synchronization problems over long sequences of identical bits. Manchester encoding. Each bit is represented by a transition, a low to high transition for a 1 and a high to low transition for a 0. This makes it easier to synchronize sender and receiver. For wireless transmission, data is encoded onto radio waves through a process called modulation, where properties of the wave, amplitude, frequency, or phase, are varied to represent data. Modern Wi-Fi uses complex modulation schemes like quadrature amplitude modulation to pack more bits into each transmission cycle. Why Layer 1 matters for cybersecurity. Physical security is the first line of defense in any security strategy. If an attacker gains physical access to a network cable, they can attach a passive tap device and intercept all traffic on that cable without the network detecting anything. This is why sensitive network infrastructure should always be located in locked server rooms with restricted access. On fiber optic connections, physical tapping is much more difficult and tends to cause a measurable loss in light signal strength, which can be detected. This makes fiber optic cables significantly more resistant to physical eavesdropping. On wireless networks, the open nature of radio frequency propagation means anyone within range can attempt to capture packets. This is why security audits of wireless networks are an important part of a penetration test, and why tools like Wireshark, which you have already used, can be used to analyze wireless traffic when the network interface is placed in monitor mode. Understanding which physical media are in use in a target environment helps a security professional assess the realistic risk of physical interception and prioritize recommendations accordingly. To summarize the key points of this chapter, Layer 1 is concerned exclusively with transmitting raw bits through physical signals. The main media types are copper twisted pair cables, coaxial cables, fiber optic cables, and wireless radio frequency. Each medium has specific characteristics in terms of speed, range, cost, and security. Signals can be analog or digital, and degrade over distance due to attenuation and interference. Devices like repeaters and hubs operate purely at this layer. Understanding the physical layer is essential for any cybersecurity professional, both for assessing physical security risks and for understanding how network traffic flows at the most fundamental level.